to introduce the brilliant representative of Georgian analysis, a group of Georgian mathematical analysis. And now the professor of King's College London, Professor Eugene Shargorodsky, or Eugene Shargorodsky. Please, Evgeny, you have 55 minutes
okay.
and 5 minutes for discussion.
Okay, thank you very much. Thanks to the organizers for inviting me. And just to clarify to the British colleagues, when Sergei says Georgian, he doesn't mean the period of King George. This is the country where I come from. This is a joint work with Lasha Ephremidze, another Georgian, and Ilya Spitkovsky. These are top people in the field. If you have questions after my talk, I'm sure they will be able to answer your questions. Right, so I will be talking about quantitative results. Well, quantitative means estimates, estimates means norms, norms means spaces. So if you are on the applied spectrum, so please accept my apologies. This might not be your cup of tea, but somehow I feel that those things are needed, and I will try to explain the stuff that I need. And so I'm not the worst here, I suppose, and it's always nice to quote someone who is well respected. So, well, you can see banner spaces, so next to computers. So hopefully you, if you are not happy with my presentation, blame Sobolev. Okay, so I'll start with a bit on Hardy spaces. So just usual notation: unit circle, unit disk. Oops, sorry, wrong one. And so the Hardy spaces. So there are, well, at least two ways to introduce Hardy spaces. One is, so one unit circle, well, this is supposed to be a circle. You're talking about LP. Here you can have, you can represent your function by a Fourier series. And so if you don't have coefficients, does it have a pointer here? Does this thing have a pointer? Ah, yeah, sorry, it does say. Sorry, it says with large letters pointer. Okay, so if you don't have coefficients with negative indices, then you say that your function belongs to the Hardy space. And so if you don't have guys with negative indices, this means that you can think of this guy as z to the power n. If there are no negative indices, you kind of expect that you can extend this analytically inside the disk. And another way of introducing the Hardy space is to say that we're talking about functions that are analytic in the unit disk. And then you look at smaller circles of radius r. R is between 0 and 1. You take the norm, LP norm, on the smaller circle, and if all these norms are uniformly bounded, that's your Hardy space. So this is a Hardy space on the unit circle, this is a Hardy space on the unit disk, and then can be identified just these things on the unit circle are just boundary values of functions at the unit circle. You can think of the radial boundary values, so you just go along the radius to the boundary, or you can think of a non-tangential limit, so you go within an angle. So every function from here has a boundary value at the unit circle almost everywhere, and you can identify boundary values and the functions. So this is the identification. So when I say a Hardy space, I will not worry about whether this is the unit disk or unit circle. You can identify them. Now, if you have not seen this canonical factorization for Hardy spaces, this might be sort of feel a little technical, but it's kind of natural thing. First of all, so we have an analytic function in the unit disk. So it might have zeros. Well, zeros cannot accumulate to a point inside if you have a non-zero function. It's uniqueness of analytic functions, but they can accumulate towards the boundary. There is a condition which I am not going to write here. It's not a very, I'm not going to use it, but the condition is that you cannot have too many zeros inside. If they go to the boundary too slowly, then you have too many, and again you have uniqueness of analytic functions. It should be just zero. It will be just zero. So the first thing, you want to factor out the zeros. So ANs are zeros, so these are ANs. And the easiest thing to do is to have this factor, Z minus AN, or AN minus Z, doesn't matter. Now, because potentially you may have infinitely many, you will have to write an infinite product. You need to worry about the convergence. And so these are Blaschke factors. So the main thing is this, the numerator, and the rest is to make sure that A, everything converges, and B, these have a very nice and important for us property, is that at the boundary, almost everywhere, the modulus of this is just 1. It's a very easy calculation. So each factor, just take this factor and substitute e to the power it at the boundary, you will see that this thing has modulus 1. And this factor simply corresponds to 0 at the origin. If you don't have it, the power m is 0. So you sort of factored out the 0. So then you can say that you take a function f, you divide it by the Blaschke product. So this will be a function, let me call it f1. So this is a function that is analytic inside and doesn't have zeros. So because it's analytic and doesn't have zero inside, log of f1 is an analytic function inside. So, well, the real part, the harmonic function, is the log of the modulus, and then you have f1. So therefore, the reason I'm writing it like this is that this is the same as log f1 at the boundary.
Yeah, you wrote it correctly, just said.
Yeah, sorry. So these two are the same because they differ by the Blaschke product, and Blaschke product has modulus 1 at the boundary. So therefore, if you just use the formula, so I want to recover this function from its harmonic, real part. So there is a formula. So for harmonic function, you have the Poisson integral, and if you want to recover the whole analytic function, I think it's called Schwartz function, Schwartz formula. So this is this formula. So it's a very familiar formula. So this recovers an analytic function from the boundary values of its real part. This is a standard function from harmonic analysis. So therefore, you sort of expect that from here, so f should be b f1, and you expect f1 to be this. this is almost true, but not completely. So what is missing here, because functions in general, they can be irregular, you may have some additional singularities at the boundary, and these are captured by this function S. This is the singular inner function, and what this does is, so this is a singular measure. So this thing, dm, so derivative is 0 almost everywhere with respect to the Lebesgue measure. So basically these two, the WHTW product and the outer function, they do not capture functions like e to the power minus 1 plus z 1 minus z. So this one doesn't have zeros inside, so it's not a WHTW product, and yet the modulus at the boundary is 1. And these are functions that come from this factor. So this is a canonical factorization of, so WHTW product, this singular inner function, they together are called inner functions, and this one is an outer function. And you can think of this as the part of the function that is responsible for the modulus, for the size. And among the functions that have the same modulus at the boundary, this is the largest one, inside is the largest one. So you can think of, if you don't like this, so just think of the following. So if you have a so you cannot recover the function uniquely from the value of its modulus at the boundary, analytic functions. There will be plenty of them, and as I said, this and that, they have modulus equal to 1 at the boundary. So the inner function, outer function is the largest. So its modulus is the largest inside among all the functions that have the same modulus at the boundary. Okay, so this is the outer functions. I will not need inner functions. I will only need the outer functions. And an important condition is that if we have a function in a Hardy space, that at the boundary log is integrable, log of the modulus. Now this is not a condition on how large the modulus is, because we know that f to the power p is integrable. It's not about the large values, it's about the small values. So if, so say for example, this function cannot be 0 on a set of positive measure. So it cannot have zeros that are sort of stronger than exponential. Okay, so this limits the size. What it says is that the zeros cannot be too strong, otherwise the whole function will be 0. Okay, so and this condition will be important throughout the talk. Okay, now the factorization that I had in the title. So suppose that we are talking about matrix functions that are in L1, and for the whole of the talk they will be positive definite. So we're talking about factorization of positive functions, matrix functions that are positive definite almost everywhere. And we also need the condition that the determinant, the log of the determinant is integral. So it means that well, we allow zeros of the determinant, so we allow matrix to be degenerate, but we need to control the size somehow, and this is exactly condition that comes from Hardy spaces. Okay, so there is a theorem that says that, so this is a spectral factorization. So any such matrix function can be factorized like this. So star here means Hermitian adjoint. So it's transposed with complex conjugation.
So and here the function
and it's just simple arithmetic, so because this is integrable, the factors have to be square integrable. So this square integrable and analytic inside, so this is basically Hardy space, and this is an outer matrix function. I explain in a second what an outer matrix function is. I explained what the scalar one is. Now, this is a Wiener-Hopf factorization, although it's probably not written in the most familiar form. So this is a plus factor, the factor that is analytic inside. Now, this one, if you just do the Schwarz reflection thing, you will see that this one is the minus factor. So this is a boundary value function, these are boundary values of a matrix function that is analytic outside. It's exactly Schwarz reflection principle. So plus factor, minus factor, and we don't have, because it's a positive definite thing, there are no partial indices. So from this point of view, it's simple. This is the thing that in the middle we have the identity matrix, what Frank called the canonical factorization. So there are no issues, I mean, the issues with partial indices in general are notoriously difficult, and you will hear about these things in the last talk today. So we don't have those issues. The issues here are the following, the difficulties are. First of all, we have very little regularity. We only assume that the function is just integrable. So we don't assume that it's bounded, etc. The second issue is that we allow zeros, degeneracies of any order. I mean, any degree. So so nth degree, whatever. Well, as long as they are sub-exponential zeros, we're fine. So we are looking at a general case from this point of view. Now, the first proof of this theorem is due to Wiener. I tried to understand the proof. I didn't sort of spend too much time, but I kind of looked at it, and I completely failed. So, and when David gave his talk at the beginning of the summer school, the first talk, he said that Wiener was notorious as a poor lecturer and a writer, and kind of I really liked what David said, because then I felt that maybe it was Wiener's fault and not completely mine, that I failed to understand the proof. Now, the second proof of Helsen and Lodenslager is very clear, but it's phrased in probability terms. So again, if you are not against the probability, then you will like the talk. But if you are, there is no better place to read the proof than the book by Litvinchuk and Spitkovsky, and there it's just a beautiful proof, absolutely. Okay, so this is the theorem. Now, in most cases, even in the scalar case, you will struggle if you want to factorize it explicitly. In matrix case, it's very rare when you can do it. So usually we're talking about approximating. So approximate the factorization, and again, Lasha Epremidze will give a talk tomorrow about their method how to do it. Now, when you are doing something numerically, obviously you would like to know how stable your procedures are. Okay, and so in many cases, so in many applications, this kind of is kind of empirical. You don't know this explicitly. So there might be some noise, there might be some error. So usually you don't know this explicitly. So you're factorizing something that is not the explicit one, it's an approximation. So obviously you would like to know whether the factors that you get are close to the true ones. So this is a stability problem, and so yes, so just to I forgot to say what an outer function is. Well, there are at least two ways of doing this. First, look at the determinant this is a scalar analytic function, and if it is an outer function, then the matrix function is called an outer function. Or you can do the following. Take all the polynomials, vector polynomials, analytic vector polynomials, multiply it by your matrix function. If what you get is dense in H2, that's an outer function. The same true, I could have used this as a definition in the scalar case as well, without showing you the canonical factorization. So, you know, if you have, say, for example, if you have a Lebesgue product, you multiply polynomials and you have a 0 always, which comes from A. Okay, so therefore, those cannot be dense in H2. So surely, if you want this to be dense in A2, you want A to not to have zeros. Turns out that if you have a factor like that, then again, you don't have density. So it's dense if and only if your function is an outer function. So it's kind of another definition of outer functions. Okay, so how about, so this is the question of stability. So the function was in L1. Suppose I approximate the function in L1. Well, it's well known that in general you don't have convergence of the factors. And this is not surprising because we have this condition that the log of the determinant should be integrable. Now imagine I'm approximating this in L1 norm, and then I take kind of on small intervals, I make this function. So they do still approximate f, but I make them kind of degenerate on small intervals. So in such ways that they're just, I mean, they're about to fail the integrability of the log of the determinant thing. So they're kind of becoming much more singular than this one. So obviously, because I need the condition that log of determinant is sufficient and necessary, so I need this condition that log of the determinant is integrable. If I approximate in L1 by functions that have that, but the logs of determinant become increasingly close to sort of not being integrable, then obviously I will not have this. We can intuitively feel this. Nevertheless, if you control the logs as well, so suppose on top of this condition, you have that logs of the determinants also converge, then you're fine. Then there is a convergence. So this result was first announced without proof by Lasha, Ephremidze, and his co-authors, and then they published a proof in 2011, but there is also a proof 2004, Barclay, who was a PhD student of Jonathan Partington from Leeds. Okay, so this is a qualitative result. So we have continuity if we have convergence in L1 norm, and we have convergence of logs of the determinant, then the factors do indeed converge. But this is a qualitative result, and if you look at the proof, you can't get information. If you're trying to do sort of numerical thing, and you want to have some sort of a quantitative information to be sure how close or far you are in terms of factors, you really need estimates. And actually, say Barclay in his paper that we're using in our work says that he could not see how his method could produce quantitative results, how it could produce estimates. Now, so this is the question. The question we're trying to address is we want to quantify this. So first, so this is the question. So we would like to have an estimate of some sort. So we want to have the estimate for the distance between factors in terms of the L1 distance between the original functions and say the logs of determinants. So any function. So can we have an estimate of any sort, but an estimate, not just a qualitative result. Now, the main motivation comes from the matrix case, but well, if you cannot do a matrix case immediately, you always start with a scalar case. So let us look at the scalar case. So suppose we have a function that is non-negative almost everywhere. The logarithm is integrable. We would like to find an outer function such that this is satisfied. Basically, we're looking for an outer function whose modulus at the boundary is the square root of this function. So this looks like, never mind factorization, never mind Wiener-Hopf. It's just a kind of question of classical complex analysis. I give a non-negative function at the boundary, so have an outer function that has this modulus at the boundary. How sort of stable is this procedure of recovering an outer function? Well, there is an explicit formula. The formula that is very, it's exactly the formula from when I showed you, the formula that I showed you when I was talking about canonical factorization of functions in the Hardy space. And if you look, if you go to, so this is the function inside, and the boundary values are, so this is not surprisingly the real part, and this is the part that is responsible for the argument, and this is the harmonic conjugate. So this is the darling of harmonic analysis. This is probably the main operator in harmonic analysis. So this is just harmonic conjugate functions. So this is singular integral. Okay, so there is an explicit formula. So if you just summarize what we have, we know the continuity is there of this mapping. So I go from F to F plus. I know there is continuity there. And I also have an explicit formula. Usually when you have an explicit formula, you hope that you can get some sort of estimate. I mean, it may be difficult, it may be easy, but if you can't do it yourself, ask your friends in harmonic analysis, maybe they will be able to help. So you hope for a formula, an estimate. The first surprise is that there is no estimate. So what you can do is you can find functions. So in L1, they have modulus less than or equal to 1. So therefore, the factors will have H2 norm less than or equal to 1. So these factors will be in the unit ball of the Hardy space. Okay? Now, you will have convergence in L1. You will have convergence of logs. But the functions, the factors, will be almost diametrically opposite to each other. So the distance between them, so they're in the unit ball, it's less than or equal to 2. You can make it as close to 2 as you like. So the message is, you can choose functions that you can make them as close as you like, and the factors will be as far away as possible from each other. Now, this is the kind of stuff that sometimes we struggle to explain to our students, that continuity and uniform continuity are not quite the same. So this is a good example where we have continuity, but we don't have uniform continuity. Now, you might think that, look, here I'm controlling the size of f and fn's and gn's, but kind of I don't control the size of the logs. All I'm saying that they are close to each other. Maybe the reason is that I'm choosing them in such a way that they're kind of exploding, and that's why we have it. Not quite. You can control logs as well. So you can control logs as well. You will still have sort of these factors quite far away. I mean, you lose the kind of precision. Now those factors will be in the ball of radius 2 pi plus 1, and the distance will be almost 2. You kind of you don't have this striking result that they're as far as possible, but kind of they're still far. So you don't have, there is no estimate, full stop. So, well, half an hour into my talk, well, kind of, so should we all go home? It's kind of maybe, but so still you want to have a positive result. So the negative result is because of the generality we don't have. We wanted to have just as little restriction as possible. Now, what I'm going to do next, I will have to introduce Orly spaces. If you are not interested, don't worry, you can think about LP spaces, and there will be results stated in LP spaces. But if you're open-minded and you have not heard about Orly spaces, that's your chance to sort of learn what those spaces are. But again, the reason I want to do Orly spaces is the following. It's kind of philosophical. It's probably not a very valid point, but for me it matters. I don't want to introduce extra restrictions. I don't mind introducing extra information. Okay? So the extra information is that every function that is integrable is actually integrable with a little bit more. So it might not be integrable to any higher power, say, it might not belong to LP with p greater than 1. But it might be, say, integrable when it's multiplied by its logarithm, for example. So, and it is well known that every function, there is a little bit of space there. It's not just integrable, it's a little bit any function. Any integrable function is a little bit better than just integrable. And you can sort of be more precise about this in terms of Orly spaces. So what are Orly spaces? So an LP space is when you take the modulus of your function to power p. That's your LP space. Orly space is just putting here a more general function. That's all there is to it, almost. So you want to have just more scope to play this. I mean, you want to have functions that, say, suppose at one end you can take an exponential function. So your function is not just LP, but it's exponentially integrable. It's almost bounded. Or you can take it very close to the other end, it's just L1, just a little bit more than L1. So, but if you don't restrict functions in any way, you need to be careful because, for example, the first difficulty is that the functions that satisfy this condition, it's not a linear space in general. Because if you have this function, e to the power t, we are talking about exponential integrability. Then if your function, say, is exponentially integrable, you put 2f there. That's the square of what you had before. So therefore, this might not be integrable. It's one thing. Another thing is that you want a norm. So how do you define the norm? So this is obviously not a norm. If you put t to the power p here, in order to get the norm, you need to take p's power root from outside of the integral. So how do you do this for these functions? Okay, so to be a little bit, so I mean, we need some a bit more information. So the functions that we take, they're all convex functions. They grow at infinity faster than t and decay at 0 faster than t. So these are called end functions. And for any such function, you have a complementary function that is defined by this formula. This is a very well-known thing from convex analysis. I personally find this, I mean, because I'm not a convex analyst, I kind of, well, at the intuitive level, I don't sort of feel this formula. Or what if this function, so it's continuous function which is convex. So it will have a derivative almost everywhere that is non-decreasing. So if you have sort of your derivative is, say, continuous, then the way to do it is you take the function, take its derivative. If it's continuous, it's non-decreasing, it's continuous, it actually will be, so suppose it's increasing, you take the inverse function of the derivative, that's the derivative of phi. So kind of, they're complementary to each other. If in the kind of smoother case, their derivatives are inverse functions of each other. So probably this is more intuitive than this formula. And the typical examples are obviously for LPs. So if you have LP, then complementary function is exactly what you have for the dual space. So this is LP and LQ. Okay. The example that I have used many times, say in estimates of Schrödinger, eigenvalues of Schrödinger operators in water waves, somehow the space, this one, pops out. So what, this is the Orly space that corresponds to it is that the function, so you are putting function here. So the function times its logarithm is integrable. So it's just slightly narrower than L1, but wider than any LP for P between 1 and infinity. So, and this is an important space in harmonic analysis because operators in harmonic analysis usually are not bounded in L1, but they are bounded from this space into L1. So this is an important case. And its dual one is in sort of space of exponentially integrable functions. Okay. And so the norm, there are two standard ways of introducing the norm. So the norm of F, one is kind of Hahn-Banach theorem, really. So to introduce, so you test your function F against all functions G for which this integral with the complementary function phi is less than or equal to 1. If you don't want to use complementary functions, what you do is the following. Now, you take a function and divide it. Suppose, remember that issue when I started with, when you multiply a function by 2, it might not be integrable. So suppose you divide by a large constant. Hopefully, this integral is finite. Okay, and then you start increasing, so decreasing your constant, and the integral grows, and at some point it hits 1. So the infimum of those constants is another norm, and they're equivalent. Okay, so these are these are the Orly spaces that I will have. Again, if you are not interested in this, there will be a result for LP spaces, and this is the more important one, I guess. Okay, and yeah, so on this page you need to read from left to right, but from the bottom to the top. Okay, so this is in our estimates we will not have optimal constants, but we will have some constants. So the constant that we'll have will be k naught, and so this is this integral times a k. K is given by this formula, and where it comes from is that, as I mentioned already, in so this harmonic conjugate operator, it doesn't go from L1 to L1. It goes from L1 to weak L1. So this is weak 1-1 estimate, and so this was proved by Kolmogorov long ago, and in the 30s, I think. And so the best constant here was found by Davis, and we can feed this constant here. Again, it's not important because we have no claim that the estimates in our estimates and constants in our estimates are sharp. It's just to show you what we have. Okay, and now this is probably difficult to understand, and I kind of, again, this is not something I have intuitive understanding of. It's just a formula. So we have a function phi, we can construct function lambda phi, and the important bit for us is that this function goes to 0, because this is something that we will have in our estimate. This is the right-hand side of our estimate. Well, just to get some feeling, so if you have the LP space, so LQ space, to the power q, this function is q's power root. So just, and again, explicit example of what this function is. And the result is here. So as I said, every function which is in L1 will belong to a certain Orly space. So this Orly space. Now the quality of your estimate will obviously depend on that Orly space. And the actual sort of, this is a good term. You don't expect anything better than that. Now, and the complicated term that involves the convergence of logarithm here, so this is where the Orlish thing manifests itself. So you will have in an estimate a function that depends on how integrable your function is. Function f, the ones that you are factorizing. And I will need this estimate, so I will copy it, and while I'm doing this, you can enjoy looking at this formula. So again, the constant here is, we have no claim that this is sharp constant, but so I'm writing this because I will need to compare the matrix valued ones to this one. Okay, so it's f plus minus g plus okay, and okay, so as you can see, that this term is always there in our estimate, and so it's a 1. So this is an estimate of the type we wanted to have. Now you can see that this is the sort of the convergence rate will depend. So this is a power in the convergence rate. It depends on how integral the function is. And so if you know that your function is bounded, then you have a result that is sort of easy to understand and kind of nice. So you have, it's fairly explicit. So the distance of these factors will be twice the distance of the initial functions plus 2.5 the distance of the logs times the norm of L infinity. So if it's a bounded function, so this is a nice estimate, and you don't expect to have anything better than that. Well, maybe you can bring constants a little bit down, but again, not much. I mean, you have 2 and 2.5 there. So it's kind of, this result is, it's okay, scalar function. Okay, now, and even that one I don't mind. Okay, as I said, so the Orlish spaces you can forget about, you can think about just this estimate. And I think it's a sort of reasonable estimate. And by the way, although we don't know about the constants, at least we know that this is the correct power here. This is optimal. You can construct, so if you take any power higher than that, if you want to have sort of better convergence, better rate of convergence, in general you can't have it. If you take anything higher, you can construct, there will be functions, so f, a function which you cannot in general, for which you cannot have a better rate of convergence. So you can have a function that is in LP, you can approximate it by functions in LP, but the distance will not go at that rate. Okay, so this rate would be sort of faster convergence. No, it does not converge at that rate. So the power here is optimal. So this is, we kind of are fairly satisfied with what we have in the scalar case. Unfortunately, what we have in the matrix case, those are probably the ugliest estimates we have ever produced. But I will try in the remaining 10 minutes, I will try to A, show you those estimates, and B, explain that it might not be entirely our fault, just lifey stuff. Okay, so matrix case. So in matrix case, I will need two new quantities. So you take logarithm with a plus, so the positive part of the logarithm of the norm. So you have logarithm determinant minus this. think of the following. So if we have, in the scalar case, suppose, so this is just modulus of f. The determinant, and f, scalar case, is non-negative, so it's just log of f. Okay, n is 1, and this is determines, again, f. So it's log of f minus the positive part of the logarithm. So it's just negative part of the logarithm, and this qf is the exponential of this. So, but in the matrix case, think of the, so this, we're talking about a self-adjoint matrix, I mean, positive and definite. So the norm depends how you introduce the matrix norm, but say standard one, so this will be the largest eigenvalue. So you have n times log plus of the largest eigenvalue. The determinant is a product of the eigenvalue. So this is the sum of eigenvalues. Each one is less than or equal to the largest one, so it's always less than or equal to n times the largest log of the largest eigenvalue. And here you have n times log plus of the largest eigenvalue, so it's always non-negative. So what this does, I mean, so we will have conditions like of this type. We will need conditions of this type, that this LF is integrable or exponentially stronger assumption. Remember, this guy is the exponential of that, of modulus of that. So these are much weaker assumptions. This is kind of exponentially stronger assumptions. So in the scalar case, I already explained what this is. And say Q of f is just 1 over f. So the message is that these conditions, they're not, again, they're not conditions on how large your function is. They're conditions on how strong the zeros are. And in the matrix case, this is interplay between the largest and the smallest eigenvalue. So this is the comparative size, or basically what we are controlling is how small the determinant is compared to the maximum between 1 and nth power of the norm. So in the matrix case, you can have a situation when one eigenvalue is huge and another one is very, very small. And obviously, this is going to make your life very difficult. And this is why the estimates are as ugly as they are. So these are my ugly estimates, but bear with me. So first of all, remember, in the scalar case, we didn't need to control the logarithm. The only additional information was that f was in LP. That's the first difference here. So in this matrix case, we also want to control how strong the zeros are. Now, if you look at the stuff in black, then everything that is not colored, everything that is black, is more or less the same what we have in the scalar case. So L1 norm of the difference, so here you are. Now, so this is a constant, well, similar to this one. Then we have the difference of logs of the norms. So this is this term. This term again, log of the ratio is log of determinant G minus log of determinant F. Again, we're talking about this term. So, and again, the power is the same, 1 over Q naught. This is exactly 1 over Q here. So these terms are what we have in the scalar case. Now, this term is what we don't have. And I'm not worried about the first one. You see, alpha is anything you can choose at will. So alpha is anything between 0 and 1. In particular, if you take it very close to 0, you have convergence that is just a little bit worse than that one. So instead of, say, power 1, you will have, these are small, right? You assume that this converges to 0. So you don't have quite the first power, but you can make it as close to that as fine. Now, the worst thing is here. Again, never mind, so this is a constant, it depends on alpha. Look at this term. You have the same norm as here. That was power 1. Now you have log. Well, when this goes to 0, this goes to infinity, and you have a negative power. That was order 1 convergence. That was power convergence, almost order 1. this is a logarithmic convergence. You went exponentially worse. So this is the rate of convergence here. It's not a power convergence, it's a logarithm. Imagine how poor this sort of convergence is. And then, so if you just to sort of assume that you want to separate the difficulties, so suppose we're not bothered about the size, we want to see the effect of how strong the zeros are. Suppose function is f, I mean f is bounded, and then, well, here, well, it simplifies a little bit, but you have, again, logarithmic convergence, rate of convergence, logarithmic, e to the power. And, well, our first natural reaction was that probably we are not clever enough. Maybe we are not doing it right. Maybe we are not, but unfortunately this term has to be there. It is there, whether you like it or not. Maybe the power is not optimal, but we might be off the optimal one by just 1 power of log. Okay, so maybe you can reduce it. And the open question for us is, what is the optimal, what is the correct exponent here? So unfortunately, the convergence is logarithmic whether you like it or not. It is. So even for 2 by 2 matrices, you will have it. And this is because of the difficulty that one eigenvalue might be huge and another one might be tiny. And this makes it so much more difficult than in the scale case. So the open question is the right. So this is what we can prove. And we have a counterexample which shows that the power here cannot be more negative. So again, this goes to infinity, log goes to infinity. So the more negative power you have, the faster your convergence is. So it cannot be more negative than this. So we might be off the optimal one by just 1 power. Right. Now, if you go exponentially, if you assume you have an exponentially stronger restriction that the function that, I mean, e to the power, whatever we had in the previous theorem, is now in LP1, then we have, again, so the same guys as before, but this term now improves. We still have log that will go to infinity, but now we have power decay to 0. Now here power is not quite as good as this one. So again, you're asking yourself, well, should this term be here? Maybe again we are not doing it right. And yeah, so if you just assume that the function is in L infinity, then just again to separate the issues of the function being big and the zeros being strong, it simplifies a little bit, but you still have this term. And again, similarly to the previous case, so this is what we have. It's not quite 1 as we have here. Ideally, you would want to have 1. So you need to, so this is a slower rate of convergence. Again, you cannot, 1 is not there. You cannot have 1. We have an example of 2 by 2 where you have 1 minus, admittedly, you subtract something smaller, so you're closer to 1, but you cannot beat this rate of convergence. Again, so another open question is, what is the correct exponent here? And so after, yeah, let me skip. So we have this for Orlish spaces, but I think I have tortured you with Orlish spaces enough already. So I mean, just to flash this at you. So this is an even uglier result. But let me end up on something positive. So if you know that both the function is, matrix function is bounded, and so this actually means, I think, that the inverse is bounded, then you recover the nice estimate, the nicest one that we had in the scalar case. So if this issue of eigenvalues not being compatible is not there, if they're both sort of bounded from above and below, then you have a nice estimate where you do have exactly the best possible rate of convergence. So it is estimated by just rate of convergence of the functions and the logs of determinant. So this is what we have. Okay, I think I stop here.
Now, questions? Yeah.
Just suppose I would like to have this nice result in matrix case, but I try to make a bit weaker the original assumption that this is canonical factorization. Probably they would have some partial indices but stable ones. Could you have something?
Look, this is a positive definite matrix function. So it doesn't, think of the scalar one. It's positive, so it doesn't have the winding number. So,
I know, but this is what I
yeah.
can skip this assumption somehow. Make this a bit weaker to have something like not positive definite, but the result is the collection of set of partial indices will be stable.
The answer is I have no idea. I mean, I don't know. And actually, my feeling is that the way we proved these results, we were looking at Barclay's proof of continuity, qualitative one, and that kind of helped us to get. And that proof, I have a feeling that it doesn't use the whole information that is there. So if you look at the details, he doesn't really use the fact that f plus is an analytic function. It kind of uses almost that its integral over the unit circle equals its value at 0. The mean value theorem just for one integral. And I have a feeling that maybe if you use the full information, maybe you resolve that open question that I said. But that is all very sort of all the techniques that we use. It goes pretty much. It relies on function being positive definite, the whole techniques. So maybe you can do something there, but you really need to achieve a kind of, you have a result and you're kind of almost satisfied. But I'm not, because I have the feeling that we don't understand this problem completely. Maybe when we do, we will be in a better position to look at non-positive definite case. I don't know.
As a compromise, I have a feeling that maybe this can be extended to the case of sectorial matrix functions, when indeed the factorization exists and partial zeros, but we'll have to think about it.
You mean locally sectorial, probably.
Well, first, just sectorial.
But then if it's sectorial, then you still will not have, or will you?
Well, you will.
Okay.
Sectorial is better than local.
The outcomes that we should.
I know. But for local sectorial, you will have partial indices, but I'm not sure. I don't know.
Yeah, you will have them, but they will be all equal between themselves.
Okay.
Globally sectorial, they're zeros.
Okay. Yeah, that's what I meant. Yeah.
Okay. Then we can.
Yeah.
I've got a comment. Sorry, pardon me. I've got a comment on terminology. Once or twice you've referred to matrices where you have a very large eigenvalue in relation to the very smallest.
Ill-conditioned.
Now, of course, in numerical analysis, that's simply a measure of the condition number.
Yeah, ill-conditioned, yeah.
And then that relates to a basic formula there, which is in the jargon is forward error is less than or equal to condition number times backward error. My question then, from a different perspective, is do these ideas in numerical analysis play a role in your rather abstract theory? Because they're fundamental.
No, they're not explicit. I mean, we don't use this condition number, but that's the same issue. Yeah. So this is the issues we are struggling with. Basically, what you do is you take the matrix function, you factor out scalar one, that is its norm. That is scalar factorization, we kind of understand. So what you just have now is a bounded matrix function. So you're now in the, but by doing that you made exactly, so this is exactly the condition number. So you made the small eigenvalue smaller by that condition number. So, and this kind of, you just put one difficulty into the other one. These are exactly those issues, although we, as kind of terminology, we don't use it in the paper.
Yeah, the point about the backward error is you're considering a slightly different problem rather than the original problem. And you want to relate those two, and that's where the condition number comes in.
Yeah.
Exactly.
Is there a way of using your techniques to actually construct stable numerical methods to work out these cost functions?
There will be a talk tomorrow about a method developed to approximately factorize these things, and it's Lasha Epremidze's talk, and I hope he will answer your question. And actually, this is exactly the type of stuff that I kind of wanted to discuss with you. So whether that method is kind of numerically makes sense, whether there are better methods, and etc. So this is exactly the issue that I wanted to discuss with you. Yeah.
More questions? If not, let's spend